Right. Just so that you know, things that we talk about now are going to affect everything that we talk about later. So this is like the foundation of how we're going to explain the entire universe. Everything that we're going to explain, we're going to use atoms and light, right? With atoms and light, we can explain everything. Is there something we can't explain? I got to think about that. How about consciousness? Because I have a feeling that consciousness may have its own particle that we haven't discovered yet, like the particle of consciousness. Maybe. I don't know. But that's the latest, but psychologists are telling me. So what do I know? So atoms, right? Talking about atome from the Greeks, thousands of years ago, they talked about something called atome, that when you cut something, let's say I cut this pencil in half, then I cut the half in half, then I cut the half in half, and I keep cutting it, eventually you're going to get to something you can't divide anymore. And that's what they call an atom, right? So we're going to be putting a little spin on those atoms, right? And after I talk about the atoms, if there's any time, we'll talk about temperature and black body radiation, which is going to be sort of weird for you. What we call black body radiation, what I call a black body, as an example, is the sun. The sun is a black body. Now you go figure that one out, right? Why would anybody call the sun a black body? There's a reason for it, so we'll get to that. All right, so let's talk about atoms. And let's get this camera thing.
I love the camera.
I know, right? Me too. I love that camera. The only thing is when I zoom it, it doesn't stay zoomed. It keeps going back. It is life. All right, so atoms are really tiny things. So what can I tell you? They're really, really tiny things. Everything that we know matter is made of atoms. Now, there's some things that are indivisible, some things that are not indivisible. So these particles that are indivisible, that you can't divide, there are particles like electrons. There's no structure within the electron itself. Protons, on the other hand, they have structure, right? So we say protons are the nucleus of this atom. So we say a proton. And believe you and I, we don't really know what a proton it really is. We don't know if it's a thing. We don't know if it's just a wave, right? So we still haven't seen a single proton in that sense. But later on, I'm going to give you guys a whole different version of reality, like something they call the quantum wave function. Imagine that everything in the universe is a part of a wave. Imagine this giant wave, like a giant ocean of waves. And every one of these things is a wave. Like a proton is like a wave on this gigantic, huge wave we call the universe. That's the quantum wave function. But right now, we're going to start explaining it to you a little differently. This is something we call the Bohr atom. Mr. Bohr atom. So the Bohr atom is a very simplistic way to explain what an atom is. Again, reality, later on we'll talk about reality, but basically we're talking about the nature of reality. What is reality, right? So a proton is divisible. In fact, there's structures within the proton itself, what we call the nuclei of the atom. Right? So this is a nuclei of atom. And a single proton, we say a single proton is called hydrogen. So this already has a name, hydrogen atom, right? This is hydrogen. Called hydrogen. Hydrogen is got a single proton, one proton. And in fact, the number of protons determine the element itself. So let me show you the periodic table of the elements. Can you guys see this? Alondra, give me one of these if you can see it. Thank you. All right, so this is the periodic table of the elements. Hydrogen, which has one proton, that's it, one proton, is on the upper left-hand side. This is one proton hydrogen. So you can write this down if you're taking notes. The number of protons determines the element. That's it. The number of protons, not the number of protons and neutrons or number of electrons, just the number of protons. That makes it really simple. So here you see H stands for hydrogen, and on top it has 1. That's called the atomic number. So the atomic number is determined by the number of protons. So when we look at the next element, 2 protons, this is helium. Helium has 2 protons. 3 protons is lithium. 4 is beryllium. 5 is boron. Carbon has 6 protons. Nitrogen 7, oxygen 8, fluorine 9, neon 10, and so on. So by the time you get down here, element number 92, uranium, has 92 protons. So the number of protons determines the element. That's it. Just the number of protons determines the element. And you know that's going to be one of the exam questions, right? Exam, quiz, whatever we give you. Number of protons determines the element. So what's inside of here? What's inside the proton? Inside a proton, particle we call quark, right? Now, a quark is an elementary particle, means it's indivisible. Like an electron is an elementary particle, right? So this is an elementary particle, elementary particle, indivisible. So we say, here there is 4. Did I say 4? I meant to say 3. 3 called Q. That's quark. So we have 3 quarks that makes up a proton. Now neutrons, which we'll talk about a little later, neutrons exactly the same as a proton basically, except we say like this, change this actually. We say these quarks are just a little different, like in the atomic world, we have these weird names, like the quarks have names like this: up quark, down quark. All right, so in a proton, we have 2 up quarks and 1 down quark. In a neutron, we have 2 down quarks and 1 up quark. So this doesn't make any difference to you right now. Just know that they're not elementary particles when we talk about protons. They have structure, right? There's stuff inside of it. All right, so this is a nucleus of a hydrogen atom. So then 1 proton, a single proton, is an atom called hydrogen. And this hydrogen atom has a proton, we say is positively charged. So that plus means a charge. So that plus is charge. Charge, like that, all right? So what the heck is a charge? It's electricity, right? It's electricity. So they say, what the hell is electricity? Good question. Remember we talked about electromagnetic radiation? We said that's what light is. Light is made of electric waves and magnetic waves, right? Well, this is like the same thing. It's like electricity with a charge. So there's positive charges, negative charges. Protons have a positive charge. Now, did somebody say, why do they call it positive? Why can't they call it negative? Because they did, that's all. The only reason they call it positive is because somebody called it positive. Otherwise, there's no, it's not like they have a bad personality. So, oh, protons are bad. They are positive or something, or negative. So it's just the opposite, that's all. Now, orbiting a proton, there's something we call an electron. So these electrons are 1,000th the mass of the protons. Right? So there's a lot less mass in an electron. Again, we don't really know about the sizes, you guys. We know that they occupy somewhere in space, but we don't really know exactly how, if they're stuff or just a wave. We really don't know, all right? So electrons are 1,000th the mass. So these guys are more massive. They have more gravity. The electrons have a lot less gravity, so they have less mass, more mass. And these guys orbit the proton. So electrons orbit the proton. Right now, in a Bohr atom, we can imagine this like a solar system, right? Like the Earth is orbiting the sun, and the sun being the proton, the electron being like a planet orbiting it. Now, this picture is not correct. It's much more complicated than that, but this is the way we're going to go about learning it, that's all. So not to worry right now. And most of you have heard about this before. So now, the electron has a negative charge, and the proton has a positive charge, right? So this, we call this electron. Like that, all right? So we say the charge of the electron and the charge of the proton are opposite but equal. In other words, even though this has a 1,000th of the mass, this has 1,000th of the mass here, this is 1,000 times more mass than this, their charge are exactly the same. They're the same strength of charge, same thing. So we say charge of electrons and protons are exactly equal, but opposite. Exactly equal, but opposite. And we can also say that same charges repel, opposite charges attract. So same charges repel, opposite charges attract. All right, so that's where we're going to start, just basics. Any questions so far? So we have protons and electrons. This is the tiniest things in nature. They make up the elements, they make up the mass in the universe. The protons are not elementary particles. The protons are particles that are made of elementary particles called quarks. There's 3 quarks, proton itself. Protons have a positive charge, we call it positive. The opposite charge of the electron, which has a negative charge, the electrons orbit the protons. And why do the electrons orbit the protons? Because they're attracted. They have an opposite charge. These guys are negative, they're attracted to the positive. And so the closer they get, the more attracted they are. The farther they get, the looser they get. So if the electron, instead of here, was like over here, then it'd be less attraction between them. The closer it gets, the more attraction. Those are the basics. And the scale that I'm giving you right now is a wrong scale. In other words, if this was the size of the proton, the electron will be a mile away, far, far away, right? That's something that we can't even imagine because we've seen pictures of protons and electrons in books, and they all appear on the same page, but they're really not on the same page. The electron is really far away. The proton is here. Electron is way over there in the next county, all right? So the scales are absolutely wrong in this board or on your books. All right, I'm ready to erase this now so we can see about this quantum physics. What is this quantum physics all about? All right, I'll start on this side.
I'm just curious as to why there's a plus sign or the positive sign after the P for proton when protons are positively charged.
That's the charge, that's all.
Yeah.
If the P with a positive, that's the charge of the proton is positive.
Right, but they are all positive, aren't they?
Yes.
Okay.
So electrons are negative.
Right.
Anyways, and protons are positive electrons are negative. Neutrons, which also are inside the nucleus of the atoms, they happen to be neutral, no charge at all. So we have neutral, positive, and negative. We have all three. Okay. All right, so let's take a look at this Bohr atom. So we have a proton again here. Now here's what we call quanta. Quanta, which quantum physics is named after. Quanta is a tiny charge. It's a discrete charge. Tiny charge, right? So now what's going on here? Let's go discrete. Okay, what is this discrete? Where does this name quantum comes from? This was an amazing thing, actually. It was discovered early in the 20th century, and it's just an amazing thing. It can't really be explained. There's no explanation for it. What there is amazement. It's just the way the universe is built. And we don't know why the universe is built this way, but it is built this way. So let's see what the deal is. The deal is that orbiting these protons are electrons. But then electrons can be in these orbits. They call these orbits. We call them states. We call them levels. And there's other names: orbits, levels, shells. These are all the same thing. This is where the electrons are orbiting the proton. So then we have more. Okay, another one here. Another one here. Another one here. And basically, it could be infinite number of orbits possible for an electron to exist. So we say this one here is orbit number 1, orbit number 2, orbit number 3, or shell 1, shell 2, shell 3, or state 1, state 2, state 3, and then we'll go orbit number 4, and so on. Now here's the deal. This is what we say quantum physics. This is what they discovered. Electrons can be in the first level here, or they can be in the second level here, but they cannot be in between the levels, right? Wow. So they can't be here. They can't be here. They can't be here. They can't be here. Cannot be here. Cannot be here. Only in those specified orbits. That's it. That's the only place they can be. So because as they get closer to the proton, they have less energy. They're more, remember that negative and the positive, they attract each other. So this negative and this positive attracting each other. The closer you are to the source of attraction, the more stuck you are, the more bound you are. All right, so these guys are all bound to the proton, and they can only be here, or here, or here, or here, but nowhere in between. Now, when they get energy, where does energy come from? Photons, right? If that energy is perfect, like exactly the amount of energy that is required to go from this level to the next level, then they will travel. They go from here to here, or go from here to here, or they go from here to here. And they make something called a quantum leap, which is an amazing thing, this quantum leap, because they don't actually travel from one orbit to the next. They disappear here, and they reappear here. How does that happen? That's right. Quantum leap is this amazing thing. They disappear from one orbit, they reappear in some other orbit. Imagine like the Earth disappeared from this orbit and reappeared in the orbit of Mars. Nowhere in between. Doesn't actually go from orbit of the Earth to the orbit of Mars. Doesn't travel. It disappears here, reappears over here. Sheesh. Right? Amazing. And you can only have these orbits and no other orbit. So each orbit corresponds to a certain amount of energy. The closer they are, the less energy they have. The farther they get, the more energy they have. So it's kind of like me on the Earth. I'm stuck here to the Earth's gravity. If you get farther, there's less sticking power between me and the Earth. As I get closer, there's more stickiness between me and the Earth, gravity. Well, in this case, it's kind of like gravity, but there's just charges attracted because they're opposite charges. And the farther they get, the more energy they have. So as they go up, right, if they move up, you have more energy. When they come down, they have less energy, like that. And they can only be in those orbits. That's it. I know, it's pretty amazing. So now there is a maximum number of electrons that can be in any one of these orbits. And so how do we determine how many electrons we can have in orbit number 1, 2, 3, 4, 5? And this applies to all the atoms, not just the hydrogen atom. So how many can we have? Well, say the number of electrons in a given orbit is equal to 2 times n to the power of 2, where n is the orbit. Okay, let's see if we can figure this out, you guys. So you guys can figure it out too. So let's say in the first orbit, orbit number 1, this one here, we can have 2 electrons, right? So how does that work? We go 2 times 1 to the power of 2. 1 to the power of 2 is just 1, 2. So you can have 2 electrons max in the first orbit, like that. That's it. If there's a third electron, that third electron has to go to the higher orbit. All right, so let's see now the second orbit. So you have 2 times 2 to the power of 2. So 2 to the power of 2 is 4 times 2 is 8. So you can have 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8 electrons. And you fill this orbit up too. You can't put any more electrons. So the next orbit, how many can you have in the next orbit, you guys?
18.
18, that's right. So it'll be 2 times 2 to the power of 3. I'm sorry, 3 to the power of 2. 3 to the power of 2. 3 to the power of 2 is 9 times 2 is 18. That's right. And how many can you have in the next orbit?
32.
How many?
32.
32.
32. And how many can you have in the next one? 5 to the power of 250. And so you can figure it out now. You don't need to memorize this. So it'll be 2, 8, 18, 32, 50, 72, like that all the way out, right? All right. Any questions so far?
Yes.
Yeah.
Where did all these electrons come from?
Where did the electrons come from?
Yeah, I mean, how many electrons are in atoms that they need multiple orbits?
It depends. There are some stars we call the white dwarfs. And each one of the atoms, each one of the protons, has maybe 1,000 electrons. So that's right, they can have 1,000 electrons. It's a special state of matter where you can have a whole bunch of electrons when room is so compact, there's not room for anything to exist. So then the atoms will have a lot of electrons. And sometimes they will have more electrons than they need. It just depends. And we're going to be talking about that. We'll talk about that in detail as to where these electrons come from. They essentially, they were made at the very beginning of the universe. And they came from energy. They exist in vacuum. The electrons, protons, everything exists in vacuum. That means empty space. is full of these electrons and protons, but they're in a form we call virtual. You're just a little bit in a hurry right now, but when we get to the creation of the universe or formation of the universe, we'll talk about this, where all the stuff that you see, you, me, Alondra, Mina, we all came from space itself.
Mhm.
Energy, when you have really high energy like gamma rays, they break up the fabric of space and they bring in something called virtual particles into reality. That's where electrons come from. That's where protons come from. That's where
Mhm.
energy. Energy has to break up the fabric. But right now, in front of your face, there's virtual particles that fill up the empty space. So empty space is not empty. It's full of what we call virtual particles. They're under virtual existence, but they can't exist because the electrons and anti-electrons coexist and they destroy each other. So they go away and they come back, and they go away and come back. We'll talk about it in detail later. All right? Any
Thank you.
questions? All right, so let's see, get a little fancier now. All right, so now we'll talk about this more actually, because we have to talk about how photons and electrons interact. The interaction of photons and electrons tells us a lot, right? What do electrons and protons do? So that's how I'm going to explain everything in the universe. Like as an example, where does the light come from? Like the light that you see right now, where does this stuff come from? Where does this light come from, right? Well, it turns out that this light that you see here is electrons going down in an orbit. When the electrons go down, they give away their energy. Remember, the higher they are, the more energy they have. When they come down, they give you energy. And that energy is light. So the light that you see is coming from those electrons that we just talked about, right? We'll get to that. All right, so let's talk about temperature right now. Temperature. So we go, what the heck is temperature, right? Before we understand temperature, though, and I understand that today's topics are a little more, they're not like something easy to digest. I understand it. So now, we talk about temperature, we say, oh, it's hot, it's cold, whatever, right? That's not a very exact way of explaining something that is very scientific. So let's see if we can get a little more exact. So what would temperature be? Before we get to the temperature itself, let's talk about two different kinds of energy. One is called kinetic energy, one is called potential energy. So what is kinetic energy and what's potential energy? So we say kinetic energy is the energy of motion. The energy of motion. So kinetic energy is the energy of motion. That's kinetic energy. So that means that my pen, because of its motion, it's got a certain amount of energy. So if it hits my hand, ouch, it just hurt. Or if you're driving your car, as you drive your car, you hit a wall, you destroy your car. That's energy, right? So as you move in your car, you have kinetic energy. Anything that is in motion, that has mass, that is in motion, has kinetic energy, all right? So it's the energy of motion. All right, that's kinetic energy. Now we have something else called potential energy. This is the energy of position in a force field. The energy of position in a force field. Now let's see what all that means. All right, so I am on the first floor. If I jump out my window, nothing really happens. It's like jumping off your chair, right? Nothing happens. All right. But if I go to the second floor and I jump out, well, as I'm going up the stairs, I am storing this thing called potential energy. As I get farther and farther away from the gravitational force, remember, this is a position in a force field. So as I go to the second floor, I jump out the window. Now I break my foot. Then I go to the third floor. I jump out. Now I break my arm and my legs. Then I go to the fifth floor. I jump out. I break every bone in my body. So now I have more and more energy stored as I go higher and higher and higher. That's the potential energy. So let's see if we can figure this out. The difference between potential energy and kinetic energy. One way to explain it is a pendulum, simple pendulum, right? So here's a pendulum. When a pendulum is motion, it's got kinetic energy, right? Like that. When it gets up here, it stops. Here it has 100% potential energy. No kinetic energy, just stopped. And then that potential energy turns into kinetic energy. Kinetic now. When it gets down here, potential energy now is 0. Right here, potential energy is 0. And then that potential energy turns into kinetic energy. Now 100% kinetic energy is stopped. So 100% potential, 0 kinetic. And then keeps doing it again. This is 0 potential, 100% kinetic. Keeps going back and forth. So potential energy is turning into kinetic energy. Kinetic energy is turning into potential energy. And I'm going to ask you guys to remember something. And I'm going to be giving, this is going to be useful forever, basically. Temperature is a measure of this, kinetic energy, right? So here's the definition of what temperature is, right? So we're mostly interested in gases. Like the sun is a big ball of gas. So I'm going to give you a definition for what this temperature is in my room, in the sun, what have you. I'm going to say temperature. Temperature is the average kinetic energy of atoms in a closed environment. So temperature is the average of all this kinetic energy of the atoms, like in my room here. Excuse me. So there's atoms all over my room here. Between me and the camera, there's a whole bunch of atoms. They're moving around all over the place. Even though I don't see them, you know, they're like invisible, right, to my eye.
I have a question.
Please.
If turbulence is like the convection cells like kind of hitting each other once like they're leaving the floor, would turbulence have a temperature or no, because it's not a closed environment?
Well, they do have temperature if they were in a closed environment. In other words, the reason I say closed environment is like the temperature of my room here is the average kinetic energy, how fast the atoms are moving here, right, in my room. And if I open the door, now the atoms outside, they have a different temperature. They're going to come in here. They're going to mix in. Once they mix in, when everything is mixed up, then you're going to get the average. Otherwise, you can't get the average. Do you follow what I'm saying?
Yeah.
That's why it's a closed environment, right? Okay. So let me see. All right. All right, can you guys see this? Oh, yeah.
Yes.
Okay, thank you. Let me show you this. I guess I'll show you this first. Okay, you guys see this? Like I have a container here. It's a gas. It could be in a balloon or it can be in a closed environment someplace. So how fast these atoms are moving around is the temperature of this container. So the atoms here are moving fairly fast, I guess. Right? Like that. Now, what about in the solid? What is that like? This is what a solid looks like. They're vibrating like that. And so when you touch your table, you go, my table is cold and my table is hot. It's because of that motion of the atoms in the table. But there, you can see them. They're like in a crystal, right? So they can't really move around very easily. Whereas in a gas, the atoms are free to move around. In a solid, they're in a structure like this. So they just vibrate. So the hotter the temperature of your table, the hotter it feels. That means the more vibration there is in the atoms of your table. The hotter environment in the summertime means the atoms are moving around faster. In the wintertime, the motion slows down. Now, as it slows down, there's a limit. This limit is called absolute zero, which means the electrons stop orbiting protons. Everything stops, all motion ceases. We say that's absolute zero. And that's 0 degrees for a new temperature scheme I'm going to give you. This is how we measure everything in a scientific way. It's called the degrees Kelvin. So let me give you this new temperature. Say absolute zero. Right? Absolute zero. This is the coldest the universe can get because all motion ceases at that point. So there's a lower limit as to how cold things can get. Absolute zero. Absolute zero. Absolute zero. All right. Is minus 273 degrees centigrade. At minus 273 degrees centigrade, all atomic motion stops. No more motion. No electrons stop in their orbit. No vibration in the solids, nothing. Absolute zero. So this is called 0 degrees Kelvin. After the Scottish scientist, Lord Kelvin. So up 0 degrees Kelvin, the sun's surface temperature is about 6,000 degrees Kelvin. And what that tells you is how fast the atoms are moving. That's what we know as 6,000 degrees Kelvin. So, oh, look at that, at 6,000 degrees Kelvin, the atoms will move this fast. Or what if the core of the sun, in the center of the sun, the temperature is 15 million degrees Kelvin, which means the atoms in the core of the sun are moving at 10% of the speed of light. So they're moving really, really fast. Like they go around the Earth in 1 second. Done. So they're moving really, really fast. And that's how we know the temperature is about 15 million degrees Kelvin in the core of the sun. In the core of some stars, it gets to billion degrees Kelvin. That means they're getting like 50% of the speed of light. So the atoms are moving really, really fast. Now, there's a reason that we cannot get to 0 degrees Kelvin here on Earth or anywhere else, really. It doesn't matter where we go. We can't get to 0 degrees Kelvin. It doesn't matter where you go. The temperature of the universe is not 0 anywhere. Empty space that we just talked about, not 0. The reason is, if you want to get something to cool down, you have to remove the heat. So to remove the heat, you have to have something colder to remove it to. If you want to get to 0 degrees, there's nothing that is colder than 0 degrees to cool it down to. So like your refrigerator, it cools down, not by cooling it, by removing the heat from your refrigerator, it cools down, right? So in the same way, you can't cool it anything down to 0 degrees. We can get close to 0 degrees, but not zero, not absolute zero, where all motion ceases. All right? Okay. That's enough of that. I want to show you guys something now. And I don't expect all of you to have an instant understanding of what I want to show you next. But I'm hoping that in time, by looking at it, that you will eventually come to understand this. Can you guys see all this? Okay. Now, I guess I should show myself first. All right, now, imagine this. Help me out here. Let's say I have a rock, this rock here, right? There's a rock. I'm going to put this rock in the oven. And I'm going to turn the temperature up. You know, I have a hot oven, maybe a 1,000-degree oven. So I'm going to put this in the oven. And when it heats up, it's hot. It's really, really hot. You can't see heat, but you can measure it. It's giving a lot of infrared heat, right? So the photons coming off it, it's hot. So it's got a temperature. Now, as it gets hotter and hotter, what happens? It starts glowing, where we can see it glow. Oh, wow, man, that thing's glowing. As it gets hotter and hotter, it glows some more. This is called a black body radiation. So a black body radiation is, the black body itself is an object that is a perfect emitter. That means it gives away all light. And it's also a perfect absorber. So you can write this down. A black body, by definition, is a perfect emitter and a perfect absorber. Or you can put down perfect absorber and a perfect emitter. So it absorbs the heat that is coming to it in the oven, and then it emits it, right? So the sun is a good example. Stars are good examples of black bodies. Even though the sun is a big ball of gas, it's very, very dense, and so it's a good approximation for a black body. So all stars in the sky are black bodies. And so let's see how these black bodies radiate. So you heat up these black bodies, right? And here I have a thermometer, and it's reading in degrees Kelvin. So I'm going to lower the temperature here, and I'm going to go to maybe a light bulb. All right, so here's a light bulb. Let's see, let me get the curve to come up a little bit. All right, so here's a curve of how a light bulb, we call incandescent light bulb. Remember the ones that burn your hand when you change the light bulb? You go, ow, 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 that one. That's an incandescent light bulb, not the LED light bulb. So how does that, what kind of a light comes out of that guy, an incandescent light bulb? Well, we take a look. What's under this orange curve is the light that we should be able to see coming out, at least relatively. So here is infrared. A lot of infrared is coming out. There is some red coming out. So this is the red that is coming out of your incandescent light bulb. It also gives you some yellow. Look at that. Also gives you some green and some blue and some violet and some ultraviolet. Look at that. So you plug it into the electricity, your light bulb, and this is what's given you. Most of the energy comes out in the form of heat. I guess in the wintertime, it's not so bad, but in the summertime, you have an incandescent light bulb. You're heating up your room. You're wasting the energy. That's why LEDs don't turn the energy that you get from an electricity plant into heat, right? So now, this is a light bulb. Now, if the temperature goes up a little higher, look what happens. It's going up a little more, right? Look at that. It's a little hotter than a light bulb. But also what happens is that if you go to the sun now, as we approach the sun, look what happened to that curve. That curve is moved to the left. So left here, this is gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. So here we have the peak now is in the green, yellow, and blue. This pretty much should tell you why we see the way we see on Earth. We're evolved with the light of the sun. This is what we're mostly sensitive to. In fact, we don't see very good in the red light. So if you put a red light in your room, you won't be able to see very well. Look at that. Now, it also gives you a lot of ultraviolet. The sun gives you lots of ultraviolet. You know that. That's how you get burnt on the beach. Also gives you a lot of heat. So all this heat is coming out, right? All the heat is coming out, and there is all kinds of stuff coming out. That's why it's a perfect emitter. Sun is a black body. It's a perfect emitter of light. It gives you all light. It gives you X-rays. It gives you gamma rays. It gives you ultraviolet, visible light, infrared, microwaves, X-rays, everything, right? The whole thing. Now, as it gets hotter, let's see what happens. When we get hotter, I got to change the scale. Okay, now it's peaking here in the blue. So now that it's peaking in blue, a star that has that much temperature, like 7,000 degrees, its color is going to be a little different too. Like the sun is going to be giving you mostly yellow and green. Remember, its temperature peak was over here. And so the sun is kind of like whitish yellow. This guy here is bluish. Now, as it gets hotter and hotter, it goes even more towards the ultraviolet. Look at that. Now, this star here is an ultraviolet star at 8,000 degrees. Most of its light is coming in the ultraviolet. However, human beings, we cannot see ultraviolet, so we can't give that a color. We can't say that star is ultraviolet color. So when you see this, okay, so most of it then for us is visible in the blue and violet. So this is going to be a blue star. There's like a blue star color here. As it gets cooler, the peak is going to move to the right. And now it's giving you mostly in the green. Let's go down temperature. This star, oopsies. This star at 4,000 degrees now is peaking in the red and orange. So this star is going to be orangish in color. So black bodies, depending on what the temperature is, and this is the surface temperature we're talking about because we can't see the center of a star. We see the surface of a star. Because of that, let's see if I put the labels on. Do we get all the labels? Well, it sort of shows the ultraviolet, visible, infrared. And so here we say the star's color is how much light this peak is giving you. Like this guy is kind of orangish. The star at 8,000 was kind of peaking over here and so on. Now, when we look at the stars, we can see what light they're giving away. Okay, so most of the light of this star is coming here in the visible towards the orange reddish. You measure it, we go, okay, I know the temperature of the star is 4,300 degrees. That's how we can tell the temperature of a star, kind of working it backwards. We go, okay, so the peak here is, you know, at whatever, it's at, you know, 6,000 or 640 nanometers. That star must be orangish in color and temperature must be 4,300 degrees. If the star is cooler, we go, okay, this star here now is given mostly in the infrared, so it's going to be a deep red color star or something like that. By looking at it with our cameras and measuring that light, we can tell the temperature. Okay, that thing is 3,700 degrees. It turns out most of the universe is acting like a black body. So that's how we can tell the temperatures of the universe, right? but it's going to be much deeper than that. As we get to the stars, it's going to be pretty deep. This is basically the most difficult it's going to get, probably. Next time it's going to be kind of neato too. We're going to be talking about how the atoms and light interact. Why do you see anything at all? Why is there any light at all? Or, we're going to be talking about all of this